Okay, looks like it's time. Welcome back, everyone, and happy almost weekend. We're about to close out the 14th week of the semester. As far as with week 15 goes, like we mentioned before, Monday we're going to be just finishing up topics. And then for the rest of the days, 29th on Wednesday and the 30th on Thursday, we'll be just completely converted over to reviewing for the final exam. As far as what we have going on, we're nearly done with the last example on this tricky unit here, real population growth. And then I think the next unit is kind of refreshing. This will be a nice one to end the course on. Logarithmic scales, earthquakes, sounds, and acids. But aside from that, the other standard roundup of our announcements are our 12th quiz is due today. I'm going to get caught up on grading everything and then convert over to grading our exam 3, get it returned back to you as soon as possible on Friday is my hope and goal, Saturday morning at the very latest. Then I'm going to start converting into all my courses, filling out the exam information, posting the last page that's going to be on the final exam, the formula definitions page, as well as sample exam exercises. So it'll be a busy weekend. I hope to have everything finalized on Sunday evening at the very latest for posting information down here. Bill, any questions with the announcements, folks, or any other questions to start us out? Okay, well, let's get started then. We left the last part of the last problem on the Unit 8C before ending class on Wednesday. And here it is. But it's one of those problems where it might be a good idea to kind of recap a little bit before just finalizing the part B. The idea with this example number 7 was we're looking into a logistic growth rate, which is going to be what we consider to be the growth rate of the country, Australia, assuming it follows the logistic growth model. We had a lot of information that we had to convey in this kind of problem. We had to work with the carrying capacity, which was 60 million. We had a 1960 annual growth rate of 2%. But when we were saying that things are growing logistically, it was assumed that this was the logistic growth rate of the problem in that particular year, 1960. So we took that, we converted it to a decimal, 0.02. We're using also at the same time, the population size of 1960 in Australia was estimated to be at 10 million. And we had two things we had to come up with. The base growth rate for the logistic growth model. And after we have that, we can estimate the logistic growth rate in the year 2020. So that's a full set of the things that we did. Part A was the trickier one, however. It wanted us to find R when it says the base growth rate. And our formula for the logistic growth model is this down below. The logistic growth rate itself was known to be at 0.02, and usually R is the unknown, so it kind of just took the whole problem and flipped it on its head. So the very first thing we did was we wrote in a new formula. We went to this one down below, and we just divided by everything we see in the parentheses, keeping the logistic growth rate in the numerator. Then, following the color coding of all the information, which is, again, pretty tricky to track, there's lots of threads going on, we put in the 1960 annual growth rate at 0.02 converted to a decimal, 1960 population size of 10 million, carrying capacity of 60 inside this whole formula, and we found that the base growth rate as per the logistic model for Australia is 2.4%. So that's the fastest it could ever grow, but that's when the population is much, much smaller than the carrying capacity. Well, again, there's a lot of stuff that happened on this problem. I think it was such a tricky problem that after reflecting on it in the last part of class, I wrote down a reminder that I'm going to use when I write the final exam that the logistic growth problem, whether it's a problem like this one or another problem on these notes, I'm going to make it for extra credit on the final exam because I feel like these problems are pretty tough to do on the homework. And if you get it down on the exam, it should be rewarding. Well, last thing to do is part B. we're finding the logistic growth rate for Australia in the year 2020 next. But the good news is, that's the thing on the left right here. The only thing that's missing to do part B was our value we have in part A now. R is 2.4%. But any questions or comments at all, folks, before we go to the next portion, part B? Okay, well, let's finalize these notes finally. When it says estimated logistic growth rate in the year 2020, we have to be really careful with this information too. So we already know that R is 2.4%, but let's say here, population. In 2020, for Australia, they said that somewhere, let's see, this line right here, it's assumed to be 26 million. So that's our new population size that we have to work with. What do we need next? We're going to use this formula down below. We're going to use the carrying capacity. So we assume that that value there is going to be as a constant. So 60 million still, whether it's 1960 or 2020. The last thing we need is the base growth rate, but that's what part A was all about. We now have it at 2.4%, but let's write it in because now if we're about to calculate it with it, it has to be written in as a decimal. So R is 0.024. Pretty much that line there, but the MyLab homework system wants it as a percentage. Makes sense for part A, but then it's kind of annoying in the next part. So now it has to be a decimal for the formula we're going to use down below. So with all that information in place, we can say logistic growth rate in 2020. The idea with the logistic growth model is as the population size gets higher and higher and higher, the growth rate drops. It'll go to exactly zero if the population size is exactly the carrying capacity. So if we use that information and we knew that in 1960 at 10 million, it was 2%, then at more than double, 2.6 times 26 million for 2020, this should be quite a bit lower than the 2%. So we're going to write this now in as take the maximal growth rate, the base growth rate R, 0.024, multiply it against 1 minus the new population size, 26 million, divided by the same carrying capacity, 60 million. I think we made a comment before that I just kind of forgot that if you drop the units, it would make sense because those are going to cancel immediately. The true unit is millions of people, really. So it looks like that's what we did in the prior problem. And then finally, at this stage, we're just plugging this into a calculator. So in year 2020, take 0.024, multiply by 1 minus 26 over 60. And that's the value if we're using the formula exactly as the author stated it. It'd be 0.0136. But then the instructions are more tricky in MyLab because if you put that answer in, they'll flag it as incorrect because it also has to be converted back to a percentage. So multiply that by times 100, and we get 1.36%. And that seems about right. If it's gone from 10 million to 26 million, it's dropped a lot from a, or hang on, I'm looking at the wrong value. Sorry about that. It's dropped a lot from the 2% down to the 1.36%. Sorry, don't look at the base growth rate. That's just the fastest it could ever possibly grow. And that finally concludes our final section here. That took a few minutes to get through. I'm glad we didn't rush through it on Wednesday's class. But any last thoughts or questions at all, folks, before we close out the section? Okay, well, congratulations. I would consider this to be probably one of the more trickier sections amongst the entire course that we've come up against. The next section, it looks tricky at first because it provides us with a lot of formulas, but the formula use is not as bad as we've seen for these kind of problems we've seen here. So let's go off to that next section. The last section of the course will be finalizing this section 8D when we come back Monday of next week. But we'll also be looking for a good stopping point so that we'll end at a natural spot and possibly convert over to reviewing for the final exam at the last part of Monday. We'll see where it ends up. So there's lots going on in this section. There's two major topics and a chemistry topic. We're going to be looking into earthquakes and sounds. Essentially, in a real sense, these are both waves that we're studying. We're interested in the energy of the earthquakes, the intensity of the sounds. And then as far as acid goes, we're going to be looking into a chemistry problem if we have time at the last part of the course, as far as pH scales go. The thing in common with all three of these ideas, earthquake magnitudes, sounds in decibels, and acidity in pH, is that these are logarithmic scales. And so our first table to kind of give us a feel of what we mean by a logarithmic scale is if we look at these magnitudes of earthquakes, if we're looking into magnitudes very less than 3, it's categorized as being a very minor earthquake. Some of these happen in Idaho, and some people notice them, a lot of people don't. Globally, these are magnitude 1 through 2, 8,000 per day. 2 to 3 is 1,000 per day for the entire planet. And this is an average since 1990. But now as you climb the magnitude, the rarity goes up by a lot, and so does the category, with more and more dire sounding words. Moderate, strong, great is 8 and up. For 8 and up magnitude, these are the ones that are almost guaranteed to be a major tragedy, probably a huge loss of life. Horrible things are almost guaranteed to happen at magnitude 9, for example. But these are pretty rare, on average 1 per year. The magnitude doesn't tell the full story of the earthquakes here. If we look into this a little bit more, it tells us the magnitude scale for earthquakes is defined so that for each magnitude, it represents about 32 times as much as energy as the prior magnitude. So this grows exponentially by times 32 in a certain sense. So a magnitude 4 to 5, the magnitude 5 earthquake is about 32 times stronger is what this is telling us. The magnitude M is related to the energy released, which is going to be capital E, by either of these formulas. Log base 10 of E is 4.4 plus 1.5 times the magnitude. The author put this here more for the sake of just completeness. But if we're focusing on the energy, which is the actual thing we're going to look into for all of our questions here, the same with the homework, then in terms of energy, if you solve for E, it's 2.5 times 10 power 4 times 10 again to the power of 1.5 times the magnitude. The author might have been able to simplify this formula if they really wanted to, but they left it in this form. So just to make the reading and the homework similar, I did the same in the notes. The unit for energy is in joules. That's a unit that we looked into briefly way back in chapter 2. And using this, we're going to look into a couple routine problems, just practicing with the formula, and then start adding more and more context as we go. Our last quiz, by the way, is based off these formulas as well. So this is essentially what quiz 13 is all about. Well, any questions at all, folks, with the logarithmic scale for the earthquakes so far, or the formulas?
Yeah, there's 2 different formulas. How do you know when to use which one?
Yeah, that's a great question. And again, it's kind of weird that the author gave both formulas because in fact, for the examples in the book, the examples in the homework, and the ones here in notes, we're actually just using this one. The major giveaway is when it asks for how much energy, it's directly referring to this right here. If they asked a question ever, what is the magnitude in terms of the energy? Then you'd want to take even this formula and solve it for M. So it's kind of a weird pair of formulas that they gave us. But does that make sense with that question there?
Yeah, so one is to find the magnitude and then one is to find the energy. So they don't find the same information, correct?
Exactly, yeah. They're both related to each other, but they're solving for different things altogether. Absolutely. Other questions at the moment? Okay, and just to emphasize again, it's weird to have two formulas. For some of the problems, we're going to really need both formulas, but for the first topic on earthquakes, we will only use this formula. In exercises, which means a final exam question would also only be using this formula to keep everything in parallel with what we're actually doing in class and the homework. So just to practice work with the formula, my first problems have no context at all. It's just saying, suppose we had a magnitude 4 earthquake, how much energy is actually then being released? This one is asking us to write this out in scientific notation, and it would be E equals, take the 2.5 times 10 power 4, copying the formula verbatim. But when it says magnitude 4, we're just throwing the 4 right in place of the M here that we see in the formula. So then it's going to be times 10 power of 1.5 times 4, which makes this problem not too bad to do by hand. You could throw this into a calculator if you prefer. For scientific notation, the 2.5 is great just the way it is. And these parentheses were not needed. The author was just organizing the information in that particular way with parentheses. So we can just say that this is times 10 power 4 times 1.5 times 4. Well, if it was times 2, that would be 3. So times 4 was going to give us a 6. Oh, hang on. That's 10 power 6. Let me try again. Times 10 power 6. Then we can go back to our exponential work way back in chapter 2. Base 10 exponentials are just going to add up the exponents. So this is 2.5 times 10 to the power 10 altogether. The unit is joules. So I'll often put that in the notes, but I'm not going to take off credit if you forgot. So if a magnitude 4 hits, that's how much energy is going to be released. Well, any questions at all, folks, with that first run through of the formula? Okay, it's not the simplest formula in the world, but once again, it's kind of refreshing to do this problem after the logistic growth problems. This is a nicer formula to run through for sure. Next question kind of relates what they were saying about the magnitude scale. It says the magnitude scale for earthquakes is defined so that each magnitude, going from say magnitude 4 to magnitude 5, represents about 32 times much energy as the prior magnitude. So one way you could estimate this is take this answer, multiply it by 32, and you know the approximate amount for magnitude 5 earthquakes energy. But that could make us lose the question in my lab. What we're really going to do is just throw it into the calculator, and then we'll check how reasonable about 32 really comes out as according to the formula. So this one we want to answer in scientific notation. I forgot to bake into the question the rounding, so we'll do 3 significant digits as well. But really, it's just more practice, same formula. Amy says, will any of the problems in my lab use the formula for magnitude? No, as well as my lab, it's really just going to be the formula for energy as well. So both exercises here on the quiz and my lab additionally, which again is weird why the author provides both, but his exercises seem to only support that one. Yeah, absolutely. Thanks for asking about that. Other questions at the moment? Okay, well, let's try this out again. It's asking again how much energy. So we'll solve for E. This will be a 2.5 times 10 power 4 times 10 to the power of 1.5 times something new. So notice every time you calculate energy, a bunch of copying until you get to the magnitude. This one's magnitude 5, so we're going to multiply by 5 here. Then at this stage, if we did the same thing as we did before, this becomes 2.5 times 10 power 4 times 1.5 times 5 is 7.5. And I made the same mistake. Let me put the 10 in first. 10 to the power of 7.5. We add that up. That's 2.5 times 10 to the power of, that would be 11.5. But here's one weird technical thing about scientific notation that I don't think has ever come up before. That's not in scientific notation because we assume that that's an integer value. So this problem we really want to throw into the calculator and rewrite this in this following form. This is going to be 2.5 times 10 to the power 11.5 gives us this value. So we're going to treat the order of magnitude as actually being 11 altogether. This wants 3 significant digits. So that means we'll take the 7, the 9, and at that digit there, we'll round up to a 1. So 7.91 times 10 power 11. Then double checking the values there. So that's our new level of energy. It's an entire order of magnitude higher than the prior earthquake at magnitude 4. So that's a lot of energy released, but any questions with that value there? Okay, so again, this is about how some of the questions in MyLab look. They're kind of fast run-throughs on these formulas. A lot of the questions didn't have a lot of context, unfortunately. The author just didn't seem to have a lot of interesting questions going on, even though the reading had a lot of interesting context. But if we want to go back to this idea, magnitude 5 is defined so that it's about 32 times as much energy as the prior magnitude 4. Let's check that out. We take that number, 7.91. Let me first put in a fraction, 7.91 times 10 to the power of 11. Keep in mind we rounded on that, so it's not 100% accurate. But then divide by this, 2.5 times 10 to the power of 10. That does in fact round up to about 32. Because of the way we wrote the fractions, the top was for magnitude 5, the bottom was for magnitude 4. This is saying magnitude 5 is really rounding to the nearest integer, about 32 times more energy released than magnitude 4. Which seems strange. It doesn't seem like there should be a lot of change going from a 5 to a 4 or vice versa. But if this is a so-called logarithmic scale on these magnitudes, then the growth of the energy is exponential. So it's exploding in growth from one level to the next. Well, we'll try this out again. This is something that real has occurred, and I had to make some corrections here. I read this just today and I realized how ungrammatical it was. And so those were what the corrections are all about. So it says, for example 2, really the same kind of idea of what we did in the last example. This happened on October 28, 1983 at 8:06 a.m. This was the largest earthquake ever recorded in Idaho. Geologically, Idaho is a pretty stable place. But this earthquake, it happened between Challis and Mackay, however we pronounce that. I've lived here all my life, and sometimes I still don't know. It had a magnitude of 6.9 is what the official records say. So we're going from a magnitude 5 to nearly a magnitude 7. Keep track of that order of magnitude. All we want to know is, once again, how much energy was released. So let's give this a try. It's another run through in the formula. Energy. In this case, this one says scientific notation, 4 significant digits, but start copying up to this point in the formula. 2.5 times 10 power 4. You could drop the parentheses if you want to. They're really not needed when we go to evaluate. Times 10 to the power 1.5 times magnitude, and the magnitude of this one at a 6.9. Instead of working it out by hand, getting to say a base 10 exponential and some integer exponent, or decimal exponent rather, we can plug it into the calculator just as it sits right here, get a value out, and here's what we're going to get. 2.5 times 10 power 4 times 10 to the power 1.5 times 6.9. So we were in order of magnitude 11 when we were at magnitude 5, but for this earthquake that occurred, almost magnitude 7, it's at order of magnitude 14. That is a humongous jump in energy released. To 4 significant digits, that would be 1, 2, 3, 4. We would round that up to a 7, 5.597 times 10 to the power 14 joules. Forgot the joules on part B of the last example as well. Energy released. So that looks like an astronomical jump in terms of energy from magnitude 5 to nearly a magnitude 7. And that was the largest one that happened historically for recorded history in Idaho. Any questions at all, folks, with that computation there? Okay, well, if we take a look into other earthquakes, some of the natural ideas you might have is, what about globally on the planet? What were some of the worst earthquakes that ever occurred? How much energy was released? So that's what we're going to take a look into next. The quiz is going to be the 2 worst earthquakes of all time in terms of magnitude. You'll find how to compare the energy on the last quiz. For this one, example 3, we're going to go to the runner-up, the 3rd worst and the 4th worst earthquake of all time in terms of magnitude. These are kind of interesting because these happened recently. So first one, this was the 2011 earthquake, and almost everyone who recalls that one thinks in terms of the nuclear reactor disaster of 2011, just mentioning the year. This one happened at 2:46 p.m. in Japan's local time. This was the so-called Tohoku earthquake. It's the 4th most powerful earthquake in recorded history, triggered a devastating tsunami, a nuclear disaster at the Fukushima Daiichi nuclear power plant, and the magnitude of that one was 9.0. So this is when earthquakes become completely scary. Almost always a gigantic disaster of gargantuan scales. And they get worse. This one happened way back in 2004, so 22 years ago roughly. And this one was just completely traumatic. It, in fact, changed the way that globally people started approaching earthquake warning and response. This was the 3rd highest magnitude earthquake in recorded history, the Sumatra Andaman earthquake. The energy released, and this is some crazy geological facts, was so massive it caused the entire planet to vibrate by as much as 10 millimeters, which is 0.4 inches. And I had to look that up a couple times when I came across this information, my research, because that seems unbelievable. But that's a fact that the geologists were able to verify with their seismographs. It's as if the entire planet Earth was struck like a bell and it vibrated. It triggered a minor earthquakes as far away as Alaska. The tsunami caused one of the most catastrophic natural disasters in modern human history. There's a humongous loss of life because of the tsunami that occurred. And this one had a magnitude 9.1. And so you'll look into even higher magnitudes that occurred in the take-home quiz, the top 1 and 2 of all time in terms of magnitude, or the worst 1 and 2, you could say. So our goal here is compare the 2004 and 2011 quakes in terms of energy released. And we'll give an answer using 4 significant digits. So that's a lot of context. For the quiz, I put in a lot of context as well, but I put this information in bold just so that it doesn't get lost. They're pretty interesting earthquakes, so there's really a lot to say about them. But any questions so far with the statement of the problem? Okay, well, when it says compare, there's a lot of different ways that you can interpret that answer. And so I'm not going to be too picky. If you make a comparison, it's good enough for me. But MyLab has something usually specific in mind when it says compare. Probably better instructions if you're going to write this as an exam question to do it exactly the way MyLab wants it to is the following. How many times more energy was released in the 2004 quake, short for earthquake, versus the 2011 quake. So really, this is what MyLab is going for a comparison kind of problem like this one. They want a comparison in terms of how many times more energy is 9.1 magnitude versus 9 magnitude. And kind of the one thing that's interesting about this problem is it sounds like they should be about the same, but actually this is quite a bit bigger of a natural disaster, even with 1/10 of a magnitude higher for their official recorded magnitude on this one. So here's how we're going to compute it. We're using that formula twice. So the computation goes like this. Energy for, if we're saying 2011, 2004 compared to 2011, we keep the order the same. So 2004 should come first. It'll be the numerator. Energy for the 2004 quake divided by the energy for the thing that came second, 2011 quake. We've done these kind of computations before, but it's been a while. I think this is something we did in chapter 2 for population density to say how much more dense one country is versus another. So now going back to the formula, that's a lot of copying, right? We're going to put in 2.5 times 10 to the power 4 times 10 to the power of 1.5, but multiply it by the magnitude. First magnitude we put in, the order matters for this kind of comparison. We go to the 2004 quake, magnitude 9.1. Now, energy for the 2011 quake, copy again all this stuff, 2.5 times 10 power 4 times 10 to the power 1.5 multiplied by magnitude for 2011, magnitude 9. But now that it's all on paper, notice one thing that's kind of nice about this computation. This part is just an automatic cancellation. So even if you put it in the calculator carefully twice, you're going to get the same value as you would if you just canceled it right here. So really the part that matters for this kind of comparison is the base 10 exponential part. That's the only part that actually influences this computation. Now at this stage, we'll put it into the calculator and get a value out. First, any questions at all, just arranging the information here from the formulas?
I do. Will it still work like if you find the energy for the first and then you find the energy for the second and then you take the scientific notions of those answers and plug them in for the energy from
Yeah,
the
absolutely.
it'll still work. And then I have another question. Why did you put the 2004 quake on the top line and the 2011 quake on the bottom? Like how do you determine which one you put where?
Yeah, that one's actually really critical, making the homework sometimes tricky for these. And pretty much the logic for that is if this thing came first in the comparison when they write out the sentence, comes first, and this one comes second, what it then means is that this one will be the top or numerator, right as space to say numerator, and this one will be on the bottom. So always maintain the exact order of however the sentence was written out. So 2004 is the reason we put it on the top is only because it came first. Does that make sense with that organization here?
Yes, it does.
Awesome. And yeah, just to come back to the first question as well, it's a good way to do this is just to divide them up, completely solve the energy released for one earthquake, do it again for the other earthquake, like you mentioned, then put them together and divide, you'll come up with the same exact answer.
Will it work if because it says to round to the fourth significant number. Is it imperative that we do that at the end, or can we do that at the end of each calculation?
Oh, that's a good point. If you break up the computation, then the rounding thing might be an issue. I would say for the purposes of my lab, if the end answer wants four significant digits, then if you break it up as energy for the 2011, energy for the 2009, and two computations, round that to maybe five significant digits or six, so that we're not losing too much accuracy in the middle. Then do the division here, and you'll be all set, rounding that to the four significant digits.
Okay, thank you.
Yeah, absolutely. Other questions at the moment? Okay, well, let's take a look now how much worse the 2004 was than the 2011 in terms of how many times more energy was released is pretty much this. So going back to this calculator, I'm going to just take whatever we've got in the numerator. Again, if you pre-compute this, let me put a 1. If you're going for this answer, then it also have that part written in as well. Just make sure you give, say, 5 to 6 significant digits, maybe 6 just for the sake of safety when you do the approximation here. But in one shot, we're not going to round in the middle. We'll just go 10 power 1.5 times 9. And that's our answer there. So we won't have it in scientific notation. We'll just round this to 4 significant digits, which will be 1, 2, 3, 4. These keep on rounding up again. So this one will round up to 1.413. The numerator had the energy unit in joules, so did the denominator. But since we're dividing, they just canceled out. And all we get is this number 1.413. But now we can interpret this answer by saying the 2011 earthquake was 1.413 times more powerful. This is in terms of energy released in joules, but I'll leave it as just a times more powerful than the 2000, or hang on, I got my values backwards, didn't I? Let me see if I can fix this. The thing that came first was the 2004. It came first in the sentence, and in the numerator, it was on top. So we should say the 2004 And 4, when we go to interpret our answer, less critical for my lab, it just wants a value, but for the notes, it's helpful to get this in the right order. The 2004 earthquake was that many times more powerful than the 2011 earthquake. Which is shocking again in a certain sense, going from a magnitude 9 to just a measly 9.1, a 0.1 tenth of an tenth increase. Doesn't seem like it should be much difference, but that's a 41.3% increase in energy. It was earth-shatteringly more powerful than even the 9.0 magnitude once we went up to a 9.1. And they get even worse. In the quiz, you're going to look at even higher magnitudes that were recorded. The top worst earthquake and the runner-up, the second worst of all time. But that's a value you'd be going for in the MyLab. And this is just our interpretation that we put down below, just to say exactly what we calculated. Any last questions or comments at all, folks, getting through this one? Okay, well, all the problems here are about logarithmic scales, but there's 3 discrete topics. Going from earthquakes, the next thing we're going to look into is acoustics, sounds themselves. And the topic is somewhat similar. When an earthquake hits right at the epicenter, a wave of energy in joules through this formula propagates as a literal wave through the planet, sometimes going vast, vast distances. And if we talk about sound, we're just talking about waves of air pressure at the same time. The formulas are different. They're a little bit trickier, so we're going to take our time with these as well in the next section. And here's what our next information is going to be for acoustics. It's organized in the same way. We have the typical intensities of sounds in terms of decibels. -10 would be sounds that are completely inaudible. And I was kind of surprised when I saw this table. This has educated me. I would have thought decibel 0 means total silence, but apparently that's not the case for this scale. 0 decibels means the softest audible sounds detectable by the average human ear. Probably talking about a young person with better hearing more often than not, I would assume. So it's anchored in terms of decibels at 0 to be the softest possible sound. Decibel 10, rustle of leaves. Decibel 20, a whisper, so it gets more and more intense as we go. And then the threshold for pain of human ear, and I guess this depends on who you ask. If you go to a concert, you might not feel that pain, but the decibels could be much higher. But our book says 90 is at the threshold for pain. Depends on the person in the context, probably. 100 is going to be a siren at 30 meters. And once you get into the 120 decibel range, I remember certain devices where you could plug in an ear pod and it might warn you if you're getting into that range. You have a strong risk of damage to the human ear. And this one's a nice kind of reference. 140 decibels is how loud a jet would be 30 meters away, where you better have your protection because you could be getting tinnitus otherwise. So that's the scale. But notice this is a logarithmic scale. And if we look into the intensity is tricky when it comes to sound. This is what makes the formulas a little bit more tricky to talk about. It's a scale relative to the softest audible sound. That comes up routinely in the formulas down here for both versions of the formulas. And all of these are just saying how many times louder or more intense is a better way to say it as intensity 1 or decibel 0, softest audible sound. It's 1 because that's 1 times itself. Rustle of leaves is 10 times louder. If you go to an ordinary conversation, that's 10 to the power 6, louder than the softest audible sound. And my speech right now is probably higher than 60 decibels, just so it can be picked up well by the microphone. That's a lot stronger, and that's pretty surprising how the scale goes. Busy traffic is at 10 power of 8, louder than the softest sound, and it just keeps on jumping in magnitude rapidly. So that's pretty impressive altogether. Now the formulas, the loudness of sound in decibels is defined by the following two equivalent formulas. And I believe in this case, we will use both. So we'll be careful with these as we go, keeping track of what we're trying to measure in each case. If we want to just come up with the decibels, then we use this formula here. It's going to be a logarithmic formula, 10 times a log base 10 of the intensity of the sound in question, divided by the intensity of the softest audible sound. So that's a tricky formula, but it'll give us the decibels, the left column. We just have to know the intensity of the sound. In other words, we have to know how many times louder is it than the softest audible sound to really use this formula. Now, formula 2, we use this formula if we're trying to solve for the sound intensity itself. So there's really two different things we're looking into. We have the loudness in decibels. That's kind of like the magnitude scale for earthquakes. We have the intensity of the sound. Sound is energy, so we're thinking of energy, same color coding as in the last grouping of problems, is a base 10 exponential divided by the loudness as a decibel measure would go into that portion. And for computing the loudness in decibels, the intensity goes in this location. But the thing that's tricky, the thing that kind of stumped me when I was practicing the very first time is you cannot ignore the intensity of the softest audible sound. That's got to be here for completion of really describing these formulas exactly as what we are trying to make them be. So that part here is part of the formulas. We can't just ditch it. Well, any questions at all, folks, with looking at both of those formulas? Okay, these formulas are tricky enough because we can't, again, just simply ditch this. Logically, it's got to be part of the formulas. That's a good idea to introduce a separate variable. Let's give a name for the intensity of the softest audible sound. I'll call it I because that makes sense. It's an intensity. It's the softest sound, so it's like the base sound that's in our scale before we go to inaudible, -10 decibels. So I want to call it I sub 0 to remind us we're talking about 0 decibel. This will be the intensity of softest audible sound. Think a pin dropping on shag carpet, something along those lines. So if we use that little variable there, we can make a slightly more convenient formula anytime that we have to use the intensity formula right here. So let me rewrite this slightly differently. You can take this thing, which is I sub 0, multiply it across to the right-hand side and say the intensity of the sound, it becomes equal to 10 to the power of loudness in decibels divided by 10, and then that whole thing multiplied by the intensity of the softest audible sound, I naught. And again, the idea was if you multiply the left side by I naught, the right side by I naught, we renamed the softest audible sound as I naught, so those cancel. And then you're solving for the intensity, much like how the energy was solved for when we were looking into the earthquake scales. So it's kind of a tricky set of formulas, The intensity of the softest audible sound being part of it is kind of what makes it a little bit extra tricky as well. And you don't have to necessarily use this formula, but I think it is convenient enough to state it in the notes and give it a try. Well, any questions at all so far, folks, with the organization of the formulas?
I just want to make sure. So it's intensity of the sound equals 10 to the power of loudness in decibels divided by 10, and then multiply that by the IO, the intensity of the softest sound.
Yeah, exactly.
Okay. And if we put that in our calculator, does the loudness in decimals divided by 10, that should be probably in parentheses, correct? So it happens separately.
Yeah, absolutely. So this whole part right here, in both of the formulas, above and below, just like you said, think of that as being in one big grouping symbol like that. Yeah,
Okay, perfect. Thank you.
you bet. Thanks for those qualifying questions, or clarifying questions rather. Let me kind of reorganize that. That's a good comment as well for the exponent there. Then go times I naught. Other questions so far? Okay, well, let's give this a try. So first thing that's tricky about this is we are this time using both formulas, and now we have to decide which formula we're using. Example 4 says, what is the loudness in decibels? And that's our keyword here. If they say loudness in decibels, it means we're using the first formula right away. What is the loudness in decibels of a sound? 1,000, and I forgot the word, times, so sorry for that other edit here. So loudness for sound that's 1,000 times as intense as the background noise in the average home. So another thing that happens with these problems is it cites these tables as well. So if this is going to be an exam question, I have to print the table on the exam so you have this information ready to go as well. Or I might just cite this line into the problem, depending on how the spacing works. So we're using this line here as part of the problem. And that's kind of unfortunate. My title's up above, so recall that that's decibels. And maybe it might make more sense to just carry this whole table down. Let's screenshot it down below. Okay, so here's our reference table once again. And now back to the problem. Example 4 says, what is the loudness in decibels of a sound 1,000 times as intense as the background noise in an average home? All we know about the background noise in an average home is that it's 10 to the 4 times as loud as the softest audible sound. Notice how that word just keeps on coming up over and over again. It's kind of interesting with these formulas. So now, to answer this question, we're going to track through this formula very, very carefully. So it's loudness in decibels. It's a base 10 logarithm, so that's the tie-in with the logs that we looked into in unit, I think that was 8b. 10 times log base 10. Let me make that fraction a little bit bigger. Now, to use this formula, they had to give us the intensity they had in mind, and that's what this was. The intensity of a sound, 1,000 times as intense as the background noise in an average home. So it's not just 10 power 4, because this 10 power 4, that's how many times louder it is than the softest audible sound. So when we put this into the formula as verbatim and as carefully as possible, here's what it looks like. We'll throw in, it's 1,000 times, so here's the 1,000 times as intense as the background noise in the average home, but that background noise is 10 to the 4 times as intense as the softest audible sound. So that word comes up. We use this as a placeholder, I naught. When we put all of that together. And then that placeholder, I naught, I sub 0, is also the denominator. The intensity of the softest audible sound goes down below here, I sub 0. And this is the formula fully evaluated. Really kind of a strange process, because one thing you'll notice right away is I naught absolutely cancels. Now, this is the weird thing about these formulas. You have to have that there. It's a relative scale, all relative to the softest audible sound at decibel 0. It's also got to be there. But if you didn't write it in, it cancels out. It all boils down to just 1,000 times 10 power 4. If you want to track the logic of the problem, use the formula as verbatim as possible. It's really got to be there. It's just that they cancel out. Kind of strange and frustrating in a certain way. It's kind of a tricky problem to put together. But any questions just to this level of putting it all together into that format?
So we're always going to have, like when it tells you the intensity of, like, say it's at the threshold for the human ear, it's always going to be like 10 to the power 9 times I to the I naught.
Exactly, yeah. So if we said 12 times as loud as the threshold for pain for the human ear, just like you said, it'll be 12 times. Go to that row, 10 to power 9. The questions are going to be targeting into this table. 10 power 9 goes here. But then that 10 power 9 is just how many times as loud as this level of sound is from the softest audible sound. So I naught goes back into the problem. And then we divide by I naught once again. Really kind of strange, right?
Yeah,
I would
that's
say the takeaway is acoustics are complicated. And for the questions to be posed to make a lot of sense, they're targeting this table specifically. But sorry, questions so far at the moment? Okay, so once again, if you're doing these questions in this kind of way, and you do it on, say, the final exam, I'd say good on you. You're treating these acoustics formulas very carefully in terms of what the decibels are or what the sound intensity is if you're using this formula. But the key fact about all of this is in the questions that we ask in this textbook, I naught cancels out in both formulas that we're going to be using, some way, shape, or form. So this is the first cancellation. If you ignored I naught and just plugged in information like this, you are getting the right answer. But I encourage you to view it in terms of these, because then you're really studying what does the formula for acoustics actually look like. It always involves that denominator being a relative scale. But now here's the next part of the process. Now we're just evaluating it. This is 10 log base 10 of 1,000 is just 10 power 3. 10 power 4 multiplies in. And then we can combine those bases and say, let me see if I can get additional space here. This is now equal to 10 times log base 10 of 10 to the power 7. And here's the next fact. Turns out log base 10 and a base 10, they actually just cancel. This whole thing is a 7. But there's no harm just double checking that in the calculator. If you put in log in this calculator, that is the log base 10, 10 power 7, you in fact get just the 7 right back. That cancellation only will occur if that's a base 10 inside of the logarithm, which is also to base 10. Change the base of the logarithm, which we'll never do in this book, and the problem falls apart. And change the base of the exponential, and that process falls apart as well. But it just so happens on this one that this is 10 times 7, so 70 altogether. But remember what we were calculating was decibels. So our answer says a sound 1,000 times intense as the background noise in an average home is 70 decibels, somewhere between busy street traffic and the threshold for pain in the, threshold for pain in the human ear. So that's our answer for that one, 70 decibels altogether. It's a very tricky process because really if you were, say, taking a shortcut through the formula, it just boiled down to take 1,000, take the background noise in the busy home, 10 power 4, that plugs in, because I naught will cancel for this form of question. Well, other questions at the moment, folks, before we try maybe one more?
I have a question. So I took 10 log, I did the log I did it in the calculator. Okay, so I did log times 1,000 times 10 to the power of 4 because the I naughts had canceled out. And I got the 7. It just gave me answer 7. So then do you always multiply that by 10 to then get the answer?
Yeah, absolutely. So this 10 right here always comes down in the formula. So you're taking 10 times whatever your full result was. So if I was writing it out in this calculator in full, it'd be kind of like you just said. Throw that 10 in, go log. This is the portion you were mentioning, 1,000 times 10 power 4. And it would drop us right at that 70. So yeah,
Oh,
that 10 is always the first part there.
okay. That's where I messed up. I only put the log in because so when you hit log, it is just log to the power of 10, right?
Yes, absolutely. It kind of depends on your calculator. Just to be double checking, let me double check with you. So if you're on, say, this calculator, log is, yeah, always base 10 logarithm. So avoid the ln, that's the base e logarithm. And same idea on this calculator as well. This one always will be the base 10 logarithm.
Okay, thank you.
Yeah, absolutely. Well, again, acoustics are pretty interesting stuff. We have a couple more questions we want to take a look into, so we might save some of these for when we come back on Monday next week. This one is going to be the loudest sound ever measured in human history was a volcano eruption, Krakatoa. That's a kind of an appropriate name for the loudest sound, crack in the name. This one was 310 decibels. And it's really hard to convey just how much energy that really is, how intense that sound is. The more you look into this problem is, it's a scientific estimate. It's a real estimate using real measurement equipment across the planet, but it's also an extrapolation. It turns out the decibel table, it caps out around 192. Once you go beyond decibels 192, the sound is so intense that a shock wave actually occurs, and it's less a wave of sound and more just air being shoved as a shock wave. So this one released a shock wave, but if we extrapolated with the decibels table and visualized it as intensity of a sound, it would have been at 310 decibels. So we'll look into when we come back on Monday, how much more powerful is that? How much more intense is it than the sound of a jet 30 meters away? That's 140 decibels. So this one was a crazy event that happened on the planet. Everybody around the planet kind of noticed this pretty much, not the entire planet, but this was noticed very far regions away. I think it said as far away as a couple thousand miles, 3,000 miles away. So that's a crazy sound we hope to never hear in our lives because that will cause unreversible damage. But before we get into that one, we're just going to do a comparison of how much louder is 95 decibel sound than a 90 decibel sound. That means we're going to use the second half of the formula down below right here. Intensity of the sound is 10 to the power of the loudness in decimals divided by 10 times the intensity of the softest audible sound. So let's pull this formula down and give it a try. And now when we do this kind of problem, there's a lot of ways to interpret this information. It's hard to tell exactly what are they asking us, but it's kind of similar when we were comparing the third worst and the fourth worst magnitude earthquakes of all time. When it says how much louder, what we're trying to determine is how many times louder is 95 decibels compared to 90 decibels. So we do the same kind of organization. The thing that came first is going to go into the numerator of a fraction. In that numerator, we're going to look into the intensity of the 95 decibel sound. And then in the denominator, we'll look into the intensity of the 90 decibel sound. So that's just the left hand of the formula that we're citing down below here. Again, same formula as our author defined, but for our purposes, the problems you'll actually calculate in MyLab, potential, say, final exam question, this is the more convenient formula, solving for the sound intensity. In fact, we're using it twice altogether. We want the intensity at 95 decibels and at 90 decibels. Well, any questions so far with just the organization? Okay, well, plugging it together, notice the change in decibels seems small, but it's just like with earthquakes. It's a logarithmic scale, so intensity grows exponentially, truly. In the numerator, we're going to go, and I wish I color code that slightly different. Let me see if I can backtrack to 95 decibels and 90 decimals, because that's the thing we're going to put here in green. For the numerator, we're going to go 10 to the power of loudness in decibels for 95 decibels. Throw in 95 divided by 10. Then multiply it by the intensity of the softest audible sound, I naught. The sound of a feather dropping on concrete. I don't know what that sound would really be in practical terms, but think along those lines. Then next, it's going to be for the 90 decibel, sound intensity through this formula is 10 to the power of 90 decibels divided by 10 times I naught once again. But just in the very last problem that we solved, notice the thing that happens. The intensity of the softest audible sound also cancels when we do these kind of specific comparison type problems. And when this formula comes up in the homework, they are as comparison problems because the author didn't supply us with enough tools to go beyond this point. Without a numerical value for I naught, we're just saying how many times louder is everything than I naught itself. But that's really how the whole scale is defined. It's all relative to softest audible sound in the first place. So once we get here, we're just plugging this into a calculator. This becomes equal to, that was the wrong pen. Let me try again. This becomes equal to, in the numerator, I can probably fit this over here, 10 to the power of 9.5. In the denominator, it's 10 to the power of 9. You can subtract these if you like, or put them in the calculator as is. I'll leave that up to you. We're going to round our answer to 2 decimal places, and that'll be our final answer on this. So take 10 to the power 9.5. Lost the home row, there we go. Divide by 10 to the power 9. To 2 decimal places, that'll be a 3.16. And so what this finally tells us is 95 decibels is 3.16. Oh, geez, hang on. Let me fix my font here. 95 decibels is 3.16 as intense of a sound as 90 decibels. So again, it's pretty shocking that it's that much stronger, more than 3 times as loud, just going from 5 decibels higher. Sounds are kind of shocking. I think it's easy to take this scale for granted. This is our ordinary human experience, but we don't often think of just how intense they are and how much the intensity is really changing until we put numbers to this, we start to realize. But any last questions or thoughts, folks, with that final answer there, the 3.16?
Sorry, I have another question.
Yeah,
This
go ahead.
this is very confusing because the formula up top says intensity of sound divided by intensity of softest audible sound equals 10 to the loudest dB divided by 10. Like, but you did it when you're computing it, you're doing that formula for both uh the two of them. So how come why doesn't it show that on that formula? Because does that make any sense what I'm asking?
So yeah, I think you're mostly looking at the main formula right here, this one here. And in that formula there, pretty much what I did to it was I gave a new name for that denominator in yellow. I called it I naught, and I multiplied it on both sides. So that allowed this to completely cancel out that entire denominator. And this is what we used right here as our formula, that part there. Because we're focusing just on the intensity, we took the intensity of the sound, solved for that numerator, and we just used that part here.
But you have it in a numerator and a denominator up top. That's where I'm getting confused looking at the formula compared to what we actually did. It's different, I feel like, because the formula
What you're
doesn't,
saying,
yeah. So that I think that's why I'm confused.
well, one way to look at it is if we kind of say put down just a fast deletable blinder. Let me update that. This is about what the FBI would use. We put down a blinder that goes kind of like that. This would be the formula used once.
Yes.
So then we had to use the formula again in this kind of way. And that number there would be the formula used a second time. And so the reason we had to use it twice is only because it was asking us to do a comparison between the two different things, which means it was much like this question here. We used the energy for the quake in 2004 once just for the numerator. So that was this original formula up on the top. But then we had to use it again because we were asked to compare the intensities of the earthquakes. So we use it again down below for the same formula up above. So we had that formula, but then we had to use it twice because we were making a comparison altogether.
Okay, I was missing, I think I was missing that part. I think I was just looking at the formula and trying to understand how we plugged in more into that formula than what I was seeing. But that makes sense now. We're doing the formula, we're like combining a step, really. We're like, instead of doing them separately, we're doing it all together.
Yeah, pretty much. And you know, that
Okay.
would have been a good way to do it as well. Use the formula once, get a number out. I think that was a similar comment you made about the earthquakes. Do the
Yeah.
formula again, get another number out, and then just divide the results. Both of your numbers would have had an I naught, and then the I naughts would have canceled, just like on paper here.
Okay, yeah, I get it now. That just threw me for a loop. I just wasn't seeing how that was the formula.
Yeah. And that's one thing that's, again, really tricky is the author provides this formula, but then it's more convenient in this formula. And then worse, all the questions he's going to ask are comparison problems. So you actually use the formula twice. So it feels like it just gets weirder and weirder as we go. A pretty tricky question. But we'll use this formula again when we come back on Monday. And let's maybe change up the strategy on Monday to separate them out in two, just to give a different take or different process for doing these kind of double use formula problems. Good way to study the problem formulas as well. But any last questions at all, folks, before we call it a night? Okay, well, thanks for all the awesome questions. Those are exactly the questions I had when looking at these kind of notes for the first time about what's going on with the formulas. We'll study them a little bit further on Monday and then turn to the review, probably midway through the class. But have a great night, folks. We'll be back to it next week.